talking about is we're going to go back to single crystal diffraction. We're going to use some of that powder diffraction stuff to iterate what's going on there. We're going to talk about how single diffraction works, and then we're going to go into the math associated with those diffractions. So just to give you an idea of where we're heading, how does single crystal diffraction work, and then we're going to have to go into some mathematical concepts that you may just need the cobweb shaken off of. Like for example, or people are familiar with Euler's equation or Euler, depending. We're going to have to hit that one again. We're going to have to talk about phase shifts. So did you guys ever talk about phase shifts in like general physics? You probably talked about, when did you talk about phase shifts? Yeah, okay. So yes, that's where it's going to come into play, and you may need to help these guys out with understanding some of that. And then we're going to get into what's known as atomic scattering or atomic form factors. So I'll explain what that all means in a little bit, but for now, let's just talk about the experiment, and we will go back. So the other thing is this picture. Do you guys have that still? If you do, grab that. We're going to talk about it in a little bit, okay? All right, so let's talk about the experiment again. So what's the difference between single crystal diffraction and powder diffraction? Yeah. Well, powder diffraction you were hoping has the same lattice. Hoping. So let's say they're both a single, like they're all the same substance. What's the difference between powder and single crystal? No, we want to have the same crystal in the powder. Yeah.
Is it not just that it's a powder?
Yes, it is a powder. If you do single crystal diffraction, you will get points that look like this in the diffractogram. For powder, you get rings. We'll talk about why those things form eventually. But it mainly has to deal with the physical state of what we're talking about. So could you describe to me what is single crystal diffraction? We could talk about a schematic. We could do a schematic, but like the experiment, how do you summarize the experiment? Let's say I'm a business guy. It's going to cost you $2,000 to run this experiment, and I'm going to go, I don't know. I don't think it's worth it. Describe it to me.
You can tell how the atoms in the crystal are aligned based on shooting a laser at it.
Not a laser.
X-rays.
Yep.
X-rays.
A beam of X-rays.
Right.
Totally not laser.
Yes.
When it hits electron density, it goes out in all these different directions, and that helps you determine.
Yes. You got your $2,000. You got 1,750. You guys didn't answer. No money for you. All right. So X-ray. So we use X-rays. We irradiate what? Yeah. A single crystal to obtain a 3D structure. This is considered the gold standard of structure determination. There is not another technique. Like, you can use NMR, and NMR is great because you can have liquids, you can look at it that way. You don't have to have a single crystal, which is really hard to grow in some cases. This gets you the end. Yeah, Lily. Solid state NMR is incredibly tricky and has something to do with magic angles in it. No, you can use it still, and it's incredibly valuable, but it tends to be outside of the realm of chemists because it's solid state, so physicists deal with it a lot of times. I do know a handful of solid state chemists that do it, and a guy who used to be a professor, I think at UNC Chapel Hill, and now he works for Bruker, does only that. He's a graduate of Fredonia too, so. Okay, rah rah Fredonia. Let's talk about the schematic now. What are some things we need in our schematic to describe the experiment that's going on? We will need a detector. Right. I don't want to draw where the detector is. Yeah, we need something to shoot X-rays. I'm drawing it as a light bulb. It's not a light bulb. There are multiple X-ray generators. Does anybody know any of these? You could do that. That would be really hard to control the quality of, so we don't really do that. Mm-hmm. Yeah, you have an X-ray tube where you generate X-rays from discharge, so that's a possibility. Yeah, you don't want to swallow just radium. You're going to have a bad time. So you have these discharge tubes. That's the main source of like the ones like when you go for medical devices that hit you with things. Have you guys ever talked about synchrotrons and cyclotrons? Okay. Brookhaven National Lab on Long Island, Fermilab, and several other spots throughout the United States use literally billions of your tax dollars for this. It is a giant device that accelerates particles, so basically a particle accelerator, to produce high energy X-rays. That is a possible source. If you had to pick the more economic option, a discharge tube over this thing, does anybody know how big these things are? Really? Miles, yeah. Which one would you pick? Discharge tube. Let's say you want to know the answer very, very well. Which one would you pick? That one. It looks very simple because I just drew a circle. It's not very good for it. You can buy or purchase beam time from these spots. So anybody can do it. You have to put in a request to do it, and they either say yes or no. So a lot of times, a lot of my friends who do crystals or make crystals, what they will do is they will buy beam time, mainly at Brookhaven because it's the closest spot to here. Right? That's in Long Island, isn't it? Okay. Brookhaven? Yeah, okay, that's what I thought. Fermilab is another one. And then there's Lawrence Livermore, which one of my friends works in the nuclear defense thing. He never can tell me what he does. He follows the rules too much anyways, so it's no fun. So anyways, got an X-ray source. We blast X-rays. Pew! Okay, what are we going to shoot them at? Yeah, we got to have a crystal here. So we're going to draw a crystal. It's on a fancy platform. I'm going to draw it like a Captain Hook, pirate hook. I really care about the way that crystal looks for some reason. Okay. Here's our single crystal. I'll draw it yellow. Now this platform called a goniometer. Have you guys ever worked with one?
We use contact angle.
Yes. Okay.
Awesome.
So what this thing can do is there's one point in this crystal that will not move, but you can rotate it. Actually, I'm sorry, I guess that point does rotate too. You're trying to keep a fixed position so this thing moves. That was a horrible description too.
So you're just spinning it?
Yeah, you're basically spinning it. Yeah, thank you. Yeah, that's better. You're spinning it around, but you're not moving it in the XY plane. You're just spinning it, trying to keep one axis stable. Yeah, Joe. Yeah. Yes. This thing here is a little spike where it's called a crystal mounting spike. What you do is you have a little bit of oil and you pick up a single crystal. You're going to have to do that for experimental physics downstairs, I believe. Have you tried it yet or no? Okay. I don't know if you'll have to do it under a microscope, but you do it under a microscope. How many people work with microscopes or have? Okay. What's the hard part with them?
Hand-eye coordination.
Hand-eye coordination, because when you move this way, it actually moves another way in there because it's bounced around. So it's very hard to mount to a crystal. So not only is it very difficult to grow a single crystal, then you have to mount it, and you have to mount it in the proper position, or else it won't work. Then you got to take that thing, you got to tighten it in this apparatus and hope the crystal doesn't fall off. You take it where it needs to go, you put it in the instrument, and you hit go. Fun. Okay, what's going to happen as we bombard this sample with X-rays? We are scattering because we are assuming that this type of technique is what? What type of scattering? Elastic. So meaning no energy is transferred. There are other types of X-ray spectroscopy that you can use where you're knocking electrons out and you're measuring stuff that way, which we will talk about eventually. But in this one, it's elastic. So some electrons are going to go, some X-rays are going to go through, and some are going to bounce off. Okay. Now there's an angle here. Looking at your diffractograms, what do you think this angle is? Oh, not the film one, but the ones with the powder stuff on it. Yeah. Not theta. What is it on the bottom?
2 theta.
It's 2 theta. What was theta again? Yes, from the Bragg equation. It's the angle from the Bragg equation. Okay. What do we need to, where are we going to put our detector here?
Right in front of the one.
Which one? Oh, this whole thing?
No, just the one.
The one that goes through it, we're gaining no information because this has not been scattered. If we go here.
The one on the side, though.
Yeah, we want our detector here. I'm drawing it as an eye. Would it be a smart idea to stare into,
You got it.
stare into an X-ray? It wouldn't be.
Is that why you drew a blind? Because the lines
I'm sorry, what's that?
are blind.
Oh, the blinds? No, that's just the iris.
Oh,
There we go.
I thought you were drawing it as
Okay.
blind.
He will be after this. The detector in most cases is an electronic detector, a counter. Now, X-rays are flying beyond this. Is that safe? No. If we did have a detector here, it would burn out. So what we do is we legitimately put a block here. So now look back at your other picture where it's that film. Katie mentioned the black spot in the center, right? That black spot is from this. It stops the beam. Scientists aren't creative in their names. What do you think that thing is called?
Beam stop.
It's a beam stop. Okay. Now, let's consider some problems. You're hitting something constantly with X-rays. As this thing rotates around, the detector might also, or the source might move, but we'll worry about that in a bit. So we keep hitting this thing with X-rays and it's bouncing them. What problem are we going to have? Hey, that's okay. We put it in a sealed box with special glass so the x-rays don't hit us. I mean more about what's wrong with our experiment right now. What's going to happen is we keep irradiating this with photons. It's going to heat up. What do you know about lattice constants as you heat things up? Yes, most of the time. There are ceramics. I won't want to touch it with a 10-foot pole. It changes, let's say that. Okay, now, what do you know about molecules as you heat things up? They're going to vibrate more. If they move around more, what happens to your resolution? Decreases. So, what are we going to do to stop that? We could stop the beam and go boop once, beep, but then we'd have to do that. You need like something like somewhere in the range of 50,000 reflections in order to build a 3D structure. So we turn something on and off 50,000 times. That's going to burn that thing out. You're in a closed chamber. That's exactly what happens. You have, we have low temp N2. So it's usually a liquid nitrogen that is boil off, it's cold. And we try to hit this thing with cool nitrogen. Okay, now when we do that though, there are a couple problems that we may introduce. You might hit the nitrogen, so that might mess with stuff. A lot of times it ionizes. What other problems would you see with that? Yeah, actually, liquid nitrogen's not too bad compared to the rest of this instrument. That's not so bad. You do have to have it. So like in a rural location like this, we got 2 places to pick from to have liquid nitrogen, which isn't great. So that's not too bad. Why does concrete crack?
Because it gets thermal shock.
Yeah, can you explain that a little bit more with thermal shock?
So, with concrete, it's the water that seeps in, and then when it freezes, since the density is less,
Yeah.
it expands and cracks it.
Right. So the freeze thaw, the temperature modification changes stuff, right?
Right.
Here, as you keep cooling it, this side might be cooler than that side. So you're going to create issues that way.
Yeah.
So that is a possibility.
So would you want like a little mild cooler?
If the more mild you get, the more thermal problems you'll run into. So
Why not just have a nice and kind of shaped family thing where you just have like jet stream
Yep.
circular?
that's what happens too. You can do that. So you're trying to cool it down, but inevitably you will heat this thing, and you get some uncertainty that happens. So we'll talk about that in a second. Before we go there, let's define what this is. So I guess I could have put it this way in my notes that I had simply written. It holds the crystal, but allows it to rotate. So another question you may ask is how many different reflections do we need? So how many diffraction patterns one need for equality? I think I mentioned it already. 50,000, you can have up like a limited 1,000. Actually, the experiment you're going to do, I don't think you even touch that number, and it's for sodium chloride, I believe. And you still, maybe it's another one, and you still get a quality structure out of that one. But somewhere in this range, but what does it really depend on? Yeah. It really depends on the complexity. And I know we've discussed this in the past, but what was originally used as the detector?
Film.
Yeah, film. So if you go back to the 70s when people were trying to solve a lot of this stuff, a lot of the people who are crystallographers are also really big into photography, like old school photography. How many people, this is going to be a fun question, how many people have actually taken a picture with film? Okay. You got a never have I ever thing, you're good. That's okay. How many people have ever developed their own film? Okay.
What's that logic?
I didn't push the button, I just got to play with the film.
That's interesting. So back in Fredonia, we had one of these in the basement, and it legitimately used film. It did have another detector on it that got added on later, but the first one that they had used film, Polaroids. There were Polaroid pictures, just like that diffraction pattern right there. And they used to use that to solve this stuff, which is amazing. But that's also why, if you look at the number of solved crystal structures over time, it's like, okay, what, 1900s, 1920, it was like nothing, maybe like a handful of them. And all of a sudden, it's going to an exponential. Big advent with different detectors, electronics, and computers. This is getting faster. Back in the 70s, you used to be given a PhD to solve a crystal structure. Now you can do it on a bench top with an instrument that is way smaller. Oops. It's crazy. Okay, so the next question. What does the output look like? So the true output is a set of diffraction patterns. And that gets assembled from collecting all the different reflections and doing some math. Okay. But we have yet to explain how we actually get the atomic positions. So question. How do we get atomic positions? So what's the first hurdle we hit with these types of experiments? What do we have to have? For single crystal, we got to get a single crystal. We have our crystal, we bombard it with X-rays. That's where we get the diffraction pattern. Okay. Does that diffraction pattern look any sort of remote chemical or atomistic interpretation at all?
I know it's like,
Oh, you hit like four.
electron stuff.
Yeah, that one.
Yeah.
Yeah.
I don't think that's what it is. It's just kind of what it looks like.
Yeah, there's dots. That's cool. What we do next is something called phasing. Which has to deal with what you're learning about in modern. You do Fourier transforms, which are real fun. I'm contemplating whether we're going to talk about, like, actually conduct a Fourier transform or not. And then we move to something more chemical. We move to an electron density map. Okay. Now, what I want you to do is check out that electron density map that we have here. This is the actual true output of what we see. These are the diffraction patterns. This is a contour map that's been sliced in half. Anybody know what this molecule is? Semi-biological in nature. Where is there a lot of electron density? Given it's in the center, yeah. What do those edges look like to you? Benzene, yep, they're phenyl rings. Go down. It's a porphyrin. It's a tetraphenyl porphyrin with a metal in the center. Yeah, sort of like hemoglobin. So it's a ring that has, can I steal your paper for a second just so I can draw the orientation, right? So nitrogen, blah, blah, blah. Nitrogen, blah, blah, blah.
Oh, yeah.
And it kind of looks like that. You were starting to get more chemical. What do you know about electron density? So let's say this is HF.
Not equally shared.
It's not equally shared. Yeah. Where does the hydrogen end in the fluorine begin? I want people to come up. Right? I've got a couple different colors. For you guys, come on up. I want you to draw the barrier. So go on up, draw the barrier. Yep. Where does the hydrogen end and the fluorine begin, and vice versa? Well, you're going fancy with dots.
Oh, yeah.
Okay. There's Aiden's. Joe, where's yours?
Where does the hydrogen begin?
Where does the hydrogen end and the fluorine begin, or vice versa, whichever way you want to go about it. We'll talk about that because this is electron density only.
Right.
They do have nodes, but that's not what we're talking about. Yeah, this is a super weird one.
It's not.
It
It has
gives
a lot of ionic
away.
characters.
Mm-hmm. Go ahead.
Yeah, it's always fun explaining that.
Well, I know because I had a student come to me in my last tutoring session.
Okay. Is there a right answer technically? No, it's electron density. Electron density is diffuse. If you look at those that map right there, it's showing the diffuseness of the electron density. It shows you where there's more of it, but deciding where things end and begin is very difficult to do with that picture. But what do we want? Like, we always want to know, we draw these little spheres, right, of where the atomic position is.
But isn't it more of
This is more realistic, and this is just a model. What we do here to transfer between the two is we use modeling. We use quantum chemical simulations a lot of times to try and figure out what do those atomic positions look like, where are they most likely to occur. And we have other definitions to talk about those things. So after we get done talking about the experimental stuff, into the next topic, when we talk about atomic positions, is that how you spell modeling? There we go, get an E. Modeling. We're going to talk about wave functions, electron density, and something called density functional theory. Because in order to go between the two, we got to get there. However, the things I want to focus on are these two. Okay. Let's talk about the pros of the technique and then the cons. Okay. Question. Pros of technique. And then we'll have cons. Give me a pro or give me a con. Yeah, Joe. Expensive. Give me another pro or a con.
Hard to interpret.
Not so much anymore. It was initially hard. Now it's not too bad. It can have some difficulty. And when you say interpret,
I mean,
look at our
diffraction pattern and then
right.
oh, how do I get to
Yeah. Electron density is fuzzy. Like our discussion here, where does one atom start and the next one begin? It's up to interpretation in different theoretical models in some cases. You guys are really negative going for all the cons. We can keep this rolling though. Give me another pro or a con. Joe? Yeah. Nothing's 100% accurate, but it is considered the gold standard. It is
50 years ago, the gold standard was the piece of pulverized metal.
Yeah, it was. But this is the technique that you're actually determining electron density. Do any of the other techniques that you guys know about actually determine the electron density? No. Yeah. Well, you know about NMR, IR, UV vis. Oh, okay. Well, you used instruments, mass spec.
I didn't use those ones.
We played with it, but the mass spec is down in the
Never mind.
Someone killed it. I'm not naming names.
Give me other pros and cons. Yeah. You can see symmetries. Symmetry is always cool. What else? Think of your experimental setup now. You have to have a single crystal. Yeah. It's sensitive to temperature. I don't know even how to spell sensitive. That's how manly I am. Sensitive, toxic masculinity, woo. All right. sensitive to temperature. Now, the temperature that's associated with these things, on that printout that we have, if you look in the corner, there are these little spheres. They're called ellipsoids. We'll talk about ellipsoids in a second, but that's how you factor in temperature. So that's basically taking your 3D or your 2D map and placing it in 3D so you can give the most probable locations of electrons. And see, it should be completely spherical for a happy, undelocalized atom. But as they start to widen, that means the electron density has become more delocalized. One other big pro. I shoot X-rays at my crystal. I turn off the instrument.
You don't destroy the crystal.
You don't destroy the crystal. You still have a crystal. It's a non-destructive technique. Yeah, it costs a lot of time too, which translates to money.
Non-destructive is like more of the beta fish.
It's pretty big. It's nice because, let's say, like for example, my collaborators just made these compounds that I'm not allowed to draw up on the board, but they absorb PFAS, and it costs a lot of money to make them. They absorb it insanely well. Now they can take that and use it.
So we,
That would keep my foot up where they did.
Yeah, one of these, yeah, it'll just leach it out of us, so it'll be okay.
Yeah, you not draw it because of
It hasn't been published yet. 1, 2, it's not my crystal structure to share. And 3, it's a very big molecule and it would take a lot of time to draw. Let's talk about those thermal ellipsoids that you have. They're also often sometimes called atomic displacement parameters or anisotropic displacement parameters. When you hear the word isotropic, what shape should be in your head? Not a triangle. That's It is still iso something, isosceles. Sphere. Yep. 3Ds. So spherical distribution. What was that? Yep. Also called atomic displacement. Parameter. Or anisotropic displacement parameter. So what these are, it's a measure and anisotropic, tropy. Why can't I say that word right now? Anisotropy.
Are you having a stroke?
Anisotropic.
There you
I swear to God, my life is like me being stuck in a barrel with a stick to talk to people. It's absolutely awful.
big smile.
Yeah, exactly. This word, anisotropy. Anisotropy. I can't say it.
What is it? What is anisotropic?
Anisotropic. See, that's word. Why is that a million times easier to say?
It's not like you lie.
Anyway.
It's where you're placing the emphasis. I think it's like anisotropic. Or
Yes, I can't. I'm going to practice. It's like how I say AJ's last name. I'm just terrible at it. Yeah. So, isotropic systems are spherical in their distribution. What does this mean then?
So it's out.
Yeah, how less spherical you are.
It's oval.
Doesn't necessarily have to be. It could be ellipsoid or it could be a plate.
there one that you guys turned?
What this tells you, though, is about delocalization. What do I mean by delocalization?
Electrons are not where they're supposed to be.
Electron
Right.
cloud.
Diffuse. So as you look at that structure, the ring, those are phenyl rings. If you notice, the hydrogens are kind of just plunked on there. The hydrogens are not actually known in this system. They just guess they're there. Because they're so small, it's hard to get good refinement unless you go to a cyclotron or a synchrotron to do that. But what do you notice about that benzene ring? Do those ellipsoids look very spherical?
No. Well, I mean, the one on the C12.
Yeah.
No, it's just angle. No.
Why does that not look spherical in that benzene ring?
They're sharing the electrons.
Yep, it's delocalized. So if you look, it looks more ellipsoid. And that's what you can gather from seeing those. So a lot of people will publish those pictures with whatever molecule or structure they're considering. And what they're trying to give you is an idea of the atomic positions and the idea of delocalization in those systems. Okay. We have 5 minutes left. Are there any questions about this? Yeah, Lily.
Can you get enough information out of this to determine the bond type? Like double bonds or something?
Yes. Yes. You sometimes have to use modeling to get there, and then the idea of what is a double bond and a single bond is also debatable. So typically what happens is you do modeling, you follow some sort of model and you say, this has a bond order of blah, blah, blah. And then you argue, is that a double bond, single bond, or triple bond? A lot of times in my realm, we just say, this is the bond order, and drop it and walk away. Because you will find that the discussion of what is a bond, next week I'm going to a conference where we're going to be a bunch of people just arguing about bonds in general. It'll be great, a lot of fun. And then we'll all go out drinking afterwards. It's perfect. Does that answer your question?